Okay, Jerome asks, how would you describe science? And how are you staying a scientist? How would I describe science? What is science? Well, I think a way to describe science, and let me preface this by saying that there are a certain set of studies that have traditionally been called science. Science got such a cool reputation that a lot of things that aren't science in the same way that science originally was attach the word science to what they're doing. So there are things that are called sciences that are not really science in the way that science was originally imagined. How was science originally imagined? It was originally imagined as a way to kind of talk formally about the world, as a way that we see in nature all kinds of things happening. The question is, can we produce a kind of human explanation of what's happening in nature? You know, we see things, I don't know, planets moving around. We see, I don't know, waterfalls falling, and we see this and that and the other, rainbows happening, all these kinds of things. We see these things happening in nature. The question is, can we produce kind of a human description of what's going on? Can we tell a story about why does a rainbow happen, as opposed to just saying there's a rainbow? Can we sort of take apart how rainbows work and talk about a mechanism for rainbows and so on? And sort of the essence of science, I think, as science was sort of originally conceived, was how do we explain the world? How do we talk about the mechanisms of things? And so science was developed particularly in areas like physics, where there was a lot of success in saying, here's a law, it's described by mathematics. Go see the consequences of this law, and that explains what you actually see in nature. That was sort of a key central part of science. Similarly, in something like biology, when you could look through a microscope and see, oh, this thing is made of this and this and this, it's again a story of how it works. What is the mechanism? How does this kind of creature, you know, digest its food or whatever else it is? It's a kind of a story of mechanism. How do things work? And I think that's sort of been the traditional essence of science, is taking what is out there in the world and saying, how do we explain it? How do we describe a mechanism for it? And that's, you know, the physical sciences, the biological sciences, chemical sciences, those are places where that kind of find the mechanism story is a story. Now, then one extends to things like, well, let's say behavioral sciences, cognitive science. Cognitive science maybe is the same sort of thing. You know, can you find a mechanism by which brains manage to do this or that? Computer science, a little different, because computer science is not really about, here's what happens in the world with computation, now understand the mechanism. It's more about studying kind of what can you do with a computer, so to speak. There is a form of computer science that I tend to call ruleology, which is just asking, pick a program at random, not a program a human wrote, just a program where you set up a set of rules, you just run them and you see what happens. That is more what should be called computer science, although the ship sailed long ago on that. Computer science is what it is. That has to be given a new name. I've called it ruleology, the study of simple rules and what they do. But that's something more like natural science applied to computers. It's like, here's what happens in the computational universe, now understand mechanisms for it. As opposed to traditional computer science, which is much more, how can you build things with computers, which is not really the traditional meaning of science. I think in, you know, as I say, it's been a little confusing because many things have attached the name science to themselves because science is thought of as being cool and thought of as being definitive, so to speak. And in a sense, why is science thought of as being definitive? It's because once you kind of know the mechanism, it's kind of like it's always going to happen that way because you know why it happens. It works really well in physics. In physics, there are good, strong laws that let you see, given that law, you can predict lots of things in physics. In biology, for example, you can do that to some extent, but there haven't been kind of sort of underlying strong laws in biology. It's more, there's this particular mechanism, this leads to this, there's that particular one leads to that, and so on. It's still a build-up kind of thing where you're talking about mechanisms, and so it sort of follows the science path, but it's not as strong, it's not building as big a tower from sort of the foundations of what's happening up to kind of what you actually observe in the world. I mean, my own efforts in both physics and recently in biology have been all about kind of how do you make it as sciencey as possible in some sense, in the sense of going from as low level of foundation, as simple a set of primitives as you can, to building up to as elaborate a description of how the world actually works as one can. Now, another thing that sort of came with the science package, at least in physics, starting in the late 1600s, was the idea that science allows you to predict things. It allows you to say, given that I know this and this, I can predict this is how this and this will happen. That's been more true in physics, the physical sciences, than it's been true anywhere else. If you say in biology, can you predict sort of in the abstract what will happen in, let's say, the course of biological evolution over the next million years, what will happen? We really can't say that much about that, or haven't been able to. I think some things I've done recently give one a little bit of more of a theory of that. But in any case, the thing that sort of got part of the science package ended up being, and we can predict. And that became, in the 1950s particularly, people started to say kind of the test of whether it's really science is whether you can make predictions and then you can verify them. You can see, did the prediction work out? Could you falsify the prediction by showing, oh, it didn't work out the way you expected, so the theory you have underneath must be wrong? That approach became very sort of popular in science. It doesn't quite work as well as you might think. And the reason is there's this phenomenon that I've studied for a long time that I call computational irreducibility. And the issue is, if you have a theory about how something works, you know the underlying rules that the system is going to operate according to, it's not obvious you can say, oh, then I know everything about what the system does. Because it could be the case that you just have to run those rules. You just have to keep running them once, twice, a million times, a billion times. And the only way you can know what the system is going to do is just to run every step in the rules for, let's say, a billion steps to see what happens. And what I found is that there are an awful lot of systems that one can invent on a computer and that one can observe in the world, in the natural world, which do have this phenomenon of computational irreducibility. You can't know what's going to happen other than by just following each step and seeing what happens. And so kind of one of the traditional kind of feathers in the cap of it's made into a science that you will be able to then jump ahead and predict doesn't really work nearly as broadly as people might think. And it's sort of a fundamental limitation on science. Now, people get misled because they say, we've turned it into a science. We know its mechanisms, so therefore we know everything about it. It's not true. It can still be the case, even though you know the underlying mechanism, to know what will actually happen on a large scale, you may not be able to work that out. You may have to just follow the steps and see what happens. Sometimes you might be able to jump ahead a little bit with a computer, but if you're dealing with, what's going to happen to sort of all the molecules of gas in a room, or all of the water particles in the atmosphere or something, that's much bigger than we can simulate on a computer. And insofar as there's computational irreducibility, the actual computation happening in the system itself is far out of reach of what we can kind of simulate on a computer and jump ahead of. So in a sense, that's a confusing aspect of science, is that from within science comes this phenomenon of computational irreducibility, which tells one that one of the things that one thought was an important feature of science, that is, being able to make these predictions, isn't really something that comes along with the bundle, along with kind of the idea of understanding of mechanisms and so on. So I think the second part of this question was, how are you staying a scientist? I'm not quite sure what that means, but the thing, in science, there have tended to be several different overall approaches to science. There's doing experiments. There's making theories. Those the sort of theory and experiment are two traditional branches of ways of doing science. When you do experiments, you set something up, you have to make it, if possible, so that you know exactly what you're putting into the experiment. I'm mixing these chemicals together in this concentration at this temperature, in this way, I'm stirring them in this fashion, and in the end, they're going to turn green and do whatever they do. But you're sort of precisely setting things up, and then you say, okay, universe, just run with what I set up, and what do you get out? And then you have to look at what comes out. You have to say, well, let me measure what came out and make a conclusion from that. So doing experiments is one sort of branch of how to approach science, is just set things up very carefully, see what the world does with what you set up, then measure what comes out. That's, and in most sciences, there is an experimental component. The other approach is theory. Say, okay, I think I know the underlying laws, or maybe I can come up with underlying laws. They're abstract laws. They're represented computationally. They're represented mathematically, whatever else. Then I take those laws as a theory, and I work out the consequences of those laws, what those laws imply for what should happen in the world. Those have been two traditional approaches. Kind of computation is something a little bit in between those. You can do an experiment on a computer. You can say, I'm going to set up this law, this theory, this rule on a computer. Then I can just run it on the computer and see what happens. I've been doing that for, oh gosh, nearly half a century now. And I've discovered lots of really interesting science by that approach of doing what is, in a sense, an experiment, but it's not an experiment with physical kinds of things. It's an experiment with just abstract things in a computer. It's a lot easier, actually, I think, because it's not like if you do a chemistry experiment or something, you have to make sure the test tube is clean and all that kind of thing. If you do an experiment with animals or something, you have to make sure your mouse is well fed that day when it does the maze or whatever. If you do experiments with people, there's even more of a can of worms. Even physics experiments, a little bit cleaner, but still a lot of detailed things about, there's a little bit of extra light that crept into my apparatus, let me put some more, black tape on this thing. There's a lot of tricky things that you have to do to get an experiment to actually work right. And, one of the things that's a big test for experiments is, can you reproduce the experiment? If you take the description of the experiment, can you run it again and get the same answer? And in many areas, that's been incredibly difficult. Particularly in the biological sciences, it tends to be very difficult to get reproducible experiments. And in behavioral science, for example, where it's, do the people do this or that thing? It's almost, it's sort of a disaster in whether you can, whether there's, people talk about sort of a reproducibility crisis of the fact that so many things in behavioral science and medical science, things like that, you do the experiment again with the description that you had, and it just doesn't come out the same way. Computer experiments are nice in that respect, because if you set the computer up to do the same thing, it will do the same thing every time. And there's a certain art to doing computer experiments well, but similar to the art of doing physical experiments well, you kind of have to set up a very clean, simple experiment. So when you get some result from the experiment, you can interpret it. You're not saying, I don't know why it did that. It must be one of the 1,000 things that I put into this experiment. One of those had the effect that produced this effect. You want to have a very simple experiment where you can see everything you put in, and then you can there's nothing hidden that you put in that you didn't have coming out. I mean, it's like, it reminds one of kind of the famous story of a sort of, you could think of it as an animal behavior experiment, this horse that people thought could do arithmetic. And, you'd ask it some arithmetic, and it would, move its foot, that number of times to correspond to that answer. But it actually turned out that the trainer of the horse was perhaps unconsciously kind of giving the horse a clue about what the number should come out to be. So that's a case where sort of there was extra stuff in the experiment that you said, well, it's just a horse, it's there, and somebody's holding the horse. But actually the person who was holding the horse was unwittingly giving extra information to the horse the experiment wasn't a clean experiment. And that's, with computer experiments, a lot easier to have them be clean experiments. But in any case, in different fields of science, there are different levels of enthusiasm about experiment versus theory and so on. In physics, for example, experiment and theory are kind of neck and neck. A lot of experiments are done, a lot of theory is done. People expect that the theory will predict experiments, the experiments will inform the theory, and so on. In something like the biological sciences, people mostly think it's all experiment, no theory. If you're doing some study, some medical test study or something like this, people say, well, just do that clinical trial and just measure it. Just see, you have 100 people in the trial, 73 of them do better and 4 of them do worse and so on. You just measure it. If you say, well, there's a mechanism, there's a theory for what's happening, people are like, we don't really care. Just measure it and see what happens. There's not really a belief that theory works in the case of biology and medicine. Actually, some recent things I've done kind of suggest how one can have a theory to some extent in biology, and actually also in medicine. I happen to be working on that right now, of trying to understand to what extent you could imagine having a formalized theory of medicine in the same way as you have a formalized theory of physics. You can't get nearly as far as with physics. Computational irreducibility kind of bites you quite quickly, but it's interesting to see how far you can get and to what extent things which are just, oh, that's a thing everybody knows about medicine, but there isn't really a theory to it, to what extent you can inject theory into that. But so different fields have different sort of amounts of theory versus experiment. And physics is one of the most successful areas in terms of theory. Now, there are other fields that perhaps aren't really sciences. I mean, computer science, as I say, there aren't really experiments in the same sense, except in these areas like rheology and so on. In mathematics, insofar as it's a science, and I'm not sure you really should call it a science as such, there are mathematical sciences which use mathematics to make their theories, but mathematics itself doesn't really have this character, or doesn't at first seem to have the character of ordinary science, where you're sort of thrown something by nature and then you have to kind of explain its mechanism. Mathematics is a bit different because it's more like you've given this formal thing and you have to see the consequences of that formal thing. You know the rules for making up geometry or something. Now let's work out what actually are the consequences of those rules for geometry. Now, I actually think that mathematics can be pursued more like ordinary science, that it is like there are laws of physics that lead to all kinds of phenomena. And in our physics project, we think we've sort of figured out what the lowest level laws, the fundamental laws, the ultimate machine code of the universe is like. And insofar as we've managed to do that, everything else is kind of like mathematics. One is building up from this underlying formal structure, this set of rules one knows, so to speak, or at least one knows the general form of those rules. And then everything about how physics works is something that in principle one could work out from those rules. Just like in mathematics, everything one's going to figure out, one in principle can work out from the underlying rules about how numbers work and things like this. So that's kind of particularly, well, in mathematics, people have tended to view it as being really a theoretical kind of thing. You're working things out formally, you're proving theorems, you're doing things where you are sort of, it's all kind of all mechanism, all explanation, all the way down. I don't think that's actually quite right. I think that mathematics really should have an experimental branch where you say, well, there are these underlying rules in mathematics. Now just work out on a computer, what are the consequences of those rules? I've done a fair amount of that. Experimental mathematics, where you're just saying, these are the rules for numbers. Now what consequences do they have? Well, they have maybe some very weird consequences where we can't yet give a narrative explanation for why it works that way. You have some thing involving primes and you notice some particular pattern and so on. It's like, well, why does it work that way? It's then a question very much like ordinary natural science, where you have to kind of drill down and say, I know what happens, now why does it happen? That hasn't been the traditional view in mathematics. In mathematics, more it has been, let's build it up. Let's see how we can build up what what must happen rather than sort of observing experimentally what does happen. So I would say that in the sort of definition of science and theory and experiment and so on, mathematics, there is an experimental mathematics that is more like traditional science that hasn't been pursued as much as it absolutely should be. Anyway, a few thoughts about the nature of science.